is the final part of Lesson 5, and we are dealing with limits of transcendental functions. And we're going to finish up our study of trig and using some algebraic tricks. And then from there, we're going to talk about the squeeze theorem in a little more detail than we did in the last section. Okay, so starting with example 9, we're going to use some tricks and properties to find limits of some trig functions. So if you look at the first one, you'll see that we're going to get an indeterminate form of 0 over 0 if we do direct substitution, because sine of 0 is 0, and 2 times 0 would be 0. So we're going to have to rewrite this in a certain form. Now, what I want to get back to is what I was saying earlier, and I do believe this was at the beginning of the second video, is these two special trig limits. So if you see something that is of these two forms, like sine theta over theta, or 1 minus cosine theta over theta, and you're doing the limit, and it's important to remember the limit has to be as theta approaches 0, you can try to use these tricks to come up with these limit values. So for example, we have 3 sine 5 theta over 2 theta. So it kind of looks like this because we have a sine function over theta here, but they don't match sine of 5 theta over theta. So what we can do is we can multiply the numerator and denominator by 5 over 5. And we are going to also at the same time take out the 3 over 2. So this is going to look like this. Let me change colors. So this will look like, let's just set it up this way first. The limit as theta approaches 0 of 15 sine 5 theta over, I'm going to leave it this way, 2 times 5. Okay? And the reason I'm doing that is because here is the important part of the ratio that I want. That is what's going to allow me to use this special trig limit right here. Okay? So I am going to pull the other constants out in front of the limit. So this is going to become 15 over 2 times the limit as theta approaches 0 of sine 5 theta over 5. So now this, oh, I'm sorry, I lost the theta here and here. Apologize for that. So now this has the proper form. So I know that limit. This limit here is going to equal 1. So I am going to have 15 over 2 times 1. So I get 15 over 2. Now I have the same thing in the next example, and I know I have an extra trig function here, but if you look at this part, I have one of the special trig limits, and if you look at this part, I have the other special trig limit. So I'm going to use my sum property and write this as two separate limits. So I'm going to have the limit as theta approaches 0 of 1 minus cosine theta over theta plus the limit as theta approaches 0 of sine 3 theta over theta. I can just break that apart because you can think of them as originally being two fractions with a common denominator. Okay, now the first one is really straightforward. That is our one special trig limit. So I know the first part of this equals 0. The second part, though, is kind of like the last example. I have a 3 theta here, but I don't have a 3 here. So I have to put the 3 in there by multiplying by 3 over 3. So I'm going to multiply this by 3 over 3. So I'm going to get 3 times the limit as theta approaches 0 of sine 3 theta over 3 theta. And so I'm going to have 3 times 1, which is 3. So that's a nice trick to use. So you want to make sure that you take the time to learn these two special trig limits. Okay, so the final part of lesson 5 is going back and revisiting the squeeze theorem. So remember, the idea is, looking at this picture, you are trying to have something like this oscillating function here that it's hard to find the limit at a specific point because it oscillates. So what we do is we trap it in between two functions like that, okay, that we can find the limit, and then we can estimate the limit of the oscillating function or whatever the function is in between. So we want to evaluate the limit using the squeeze theorem of the limit as x approaches 0 of x squared times sine 1 over x. So why can't we use the product rule? And it has to do with the sine of 1 over x. We're going to have an undetermined form. So the first part isn't a problem. We're going to have the limit as x approaches 0 of x squared, and we can direct substitute, times the limit as x approaches 0 of sine 1 over x. And of course, this limit does not exist. So we're going to have to try something else. So that's why we cannot use the product limit law. Okay, so what do we do instead? We do something like this. We can consider the domain of the sine function. So actually, we're going to, as you know, the sine function has to be anywhere between -1 and 1. Okay? So we know that's true for the values. So it doesn't matter what x you put in there, we can get a y value that is somewhere between -1 and 1. That's the way the sine function looks. So we can conclude then, putting any x in there, that the sine of 1 over x has to also be between those two values. So since that, what we can do then is we can start with that idea. And we're going to multiply through everything with an x squared. And when we do that, we get that we have a negative x squared is less than or equal to x squared sine 1 over x, which is less than or equal to x squared. So now what we have done is we have squeezed our original function, x squared times 1 over x, sine of 1 over x, in between two well-defined functions that we can find the limits of. So that's what we're going to do next. So we are now going to say that we know that the limit as x approaches 0 of negative x squared is going to equal the limit as x approaches 0 of x squared, and that is equal to 0. So by the squeeze theorem, the limit as x approaches 0 of the function that's squeezed in between them has to also equal 0. So that's how the squeeze theorem is used. Let's do one more example. So the next one now, we have our x squared there, but we also have cosine 1 over x. So again, revisiting the idea that we know that the cosine function falls in between, and I'm going to use theta instead of x this time. It might be a little less confusing. That it doesn't matter what theta is, since we have no transformations, the values we can get when we substitute a value in for theta has to be some y value between and including -1 to 1. So we start with that idea. So if that has to be true, then we can say that since we can have any theta, why not make theta 1 over x squared? And now the cosine 1 over x squared is multiplied by x squared. So we're going to multiply everything through by that. And so we get -x squared less than or equal to x squared cosine 1 over x squared is less than or equal to x squared. And now we can make the same argument because we have the same idea. We have our function squeezed in between two well-defined functions, -x squared and x squared. So we can say then that the limit as x approaches 0 of -x squared is going to equal the limit as x approaches 0 of positive x squared, and they're equal to 0. So we know that our limit has to be squeezed in between these two. So we're squeezed in between 0, and it's 0 on both sides. Therefore, can't get the little dot to work for me. Therefore, there we go. Therefore, by the squeeze theorem, the limit as x approaches 0 of x squared cosine of 1 over x squared equals 0. So that's the whole idea. You want to try to use a well-defined function or two different well-defined functions and squeeze your function in between the two to find the limit. Okay, so that's the end of lesson 5. I will take any questions in class, and good luck.